Okay, so there's something a little bit wrong with this one. It's not terrible, but a little bit wrong. What do I notice? Here's my original function, here's my antiderivative. And the domains are much different. Okay, here the domain is, let's do a colon instead, x not equal to 0. That's my domain there. Here, the log function here can only accept x is bigger than 0. That's a big difference between the two domains. So what we're going to do is we're going to say, well, what if I do something like what if I put an absolute value on that ln of x? Is that going to work? Is that going to work as an antiderivative here? Let's check to see if that works. Hint, yes, it does work, but let's see why. F prime of x. Okay, before I check, let's just motivate this. What am I doing here? I said the domain wasn't big enough, right? Here this domain here is much bigger than this one, so I would like to have the domains match as much as possible. So by putting the absolute values here, the domain is, now it's x not equal to 0. Because now I can put negative numbers in here. They won't cause a problem because the absolute value sign is there. Okay. Let's return to my check here. Check. F prime of x is the derivative of ln absolute value of x plus c. Now, there are two cases. X is either bigger than 0 or less than 0. So if x is bigger than 0, then f prime of x equal to the, you can drop the absolute value. Okay, because if x is bigger than 0, then this absolute value is redundant. I don't need it. So I get just 1 over x plus 0. And that is indeed correct. Okay, this does indeed equal just f of x. Now I should check the other case to make sure this still works. F prime of x is, now the absolute value does something different. Now I have x as a negative number, so this absolute value is going to make that negative number into a positive number, and it's going to do so by sticking another negative in front. And now I do the derivative, and I get negative 1 over negative x plus 0, which again does equal 1 over x. That does work again. Okay, long story, but the upshot is that this will be our most general antiderivative for f of x equals 1 over x. Okay. Let's do some more exercises here to practice doing antiderivatives. How many do we? Oh, we've got a whole bunch here. Let's try to get it nicely zoomed here. Okay, that's good right there. Okay, pause the copy. I want you to try all these, and I will go through them one by one right now. But you should try, because if you try now, then you'll have to do less trying later. Okay, secant squared, the antiderivative, tan, right? Tan of x plus, now the 3 is just going to stay up front. And then I'm going to have ln absolute value of x, and then my plus c on the end. Okay, not sure what to do with the 3. Well, when in doubt, try something, check it by doing a derivative, and move forward. Next one. Okay, what function has 1 as its derivative? Well, it's just going to be x, right? And then for the other ones, I use my formula. The formula being, if you have x to the n, you're doing an antiderivative, you use this formula, x to the n plus 1 over n plus 1 plus c. So we're using this one over and over and over again, both in Cal 1 and in Cal 2. This guy is going to be beaten absolutely to death. You'll see it in your dreams. Hopefully not as a nightmare. Okay, so I used this formula 4 times, actually, because I guess you could think of it as, 1, this 1 here. If you really want to do this, that's x to the 0. So that'd be x to the 0 plus 1 over 0 plus 1, which is x. I don't know if that's useful to you. If not, just throw it away. Tan squared. Oh, tan squared. Tan squared, tan squared. I don't know. What is tan squared? I don't know. This one's tricky. I have to use a rule, right? I have to use, what is the rule? Secant squared is equal to tan squared x plus 1, which tells me that tan squared is equal to secant squared x minus 1. So this is a trig identity I'm using. Then the antiderivative of this is going to be the antiderivative of this. So that's tan x minus x plus a constant. So this is a trig identity. Okay, cosecant, cotangent, this is just a matter of memorizing the derivative of cosecant. I have to throw a negative in there to make it right. This one here, tricky, a little bit tricky. There's a couple things happening. E to the x is its own derivative. The next one is in fact one of these n plus 1 things. It looks like something else, but it's not. E times x, well, I'm going to have e times the antiderivative of x. And finally, which function has this as its derivative? Well, that's so easy, it's hard. It's e times x. Root x. This equals x to the half. So f of x is going to be, again, using this rule, x to the n plus 1 over n plus 1 plus c, which is 2/3 x to the 3/2 plus c. Oof. So this, number 7, capital F of x, is, I would leave the 3 out front, and then I get x to the n plus 1 over n plus 1. So that's 6 over 7, x to the 7/2 plus c. So maybe for your notes, this is x to the n plus 1 over n plus 1. So that formula just never goes away. 8, the trick is to expand it out first. X squared plus 3x plus 2. So capital F of x will be x cubed over 3 plus 3x squared over 2 plus 2x plus constant. Finally, this guy I need to break up into 3 fractions. In the obvious way. I should simplify each one. Here I got 8x plus x to the, this would be minus 1/2. This one I can, factor it just to emphasize what's happening next, or to clarify what's happening next, which is to take my antiderivative, capital F, equals 4x squared 2 x to the 1/2 minus 7 ln absolute value of x. Don't forget your absolute value. I will remove a half mark every time. Okay, here I did, I used the formula x to the n plus 1 over n plus 1. I've been doing this for a few decades now, so I can do it in my head. You will too, with just a bit of practice.